Hi dear, this is Kamal Sarma. Today I am again talking about bending moment and shear force diagram. Okay, so in case of bending moment and shear force diagram on a beam, first of all you need the reactions. Always, when you have the problem, you think about finding out the reactions first because you need to know all the forces in the beam. Say this is your beam, you have simply supported, that means this side is hinge and or pin supported, the other side is roller supported. That is the definition of simply supported beam. Though in problems sometimes you will see something like this, two supports like that, but this is this is true, this is not, because it is not the reactions are always vertical. Reactions, there is a horizontal part of the reactions also, but what happens, as because our forces are vertical, there is no horizontal component of the reaction. Always remember that. Even if somebody show you the beams like that, actual beam is like this. Okay, today last class I discussed about the concentrated load like this. Today I will be discussing about the uniformly distributed load. What is it? Is called uniformly distributed load. Simply, in short form, it is called UDL, uniformly distributed load. It is expressed as, suppose if you expressed as W, a value per unit length. What is W? W is the load per unit length. That means the load may be, and it is shown like something like a cloud. And sometimes the uniformly distributed load are shown like a small arrows, something like this. This is your beam, this is your support, and they are shown as small arrows. Meaning is same. This is uniformly distributed load and say W. Okay, but what is W in SI unit? Say it is 5, let us reduce it, make it 2 kilonewton per meter. Or if you are the American system, say it is 2 kip per meter, per feet. As I told you earlier, these two units are not same, they are different. But now, what is this? What is the uniformly distributed load? Where from it comes from? Okay, so suppose that example, you have a beam. The cross section is a rectangular cross section, right? So the beam has the depth is say 1 meter and this is width is 0.5 meter. Or if you take the American system, foot pound, say it is 3 feet. I'm putting 3 feet because 3 feet is almost equal to 1 meter. So it is say 1.5 feet. This is say concrete. So unit weight, that means the weight of concrete is in American systems 150 pound per feet or 0.15 kip per feet. That is the American unit weight of the concrete. For SI unit, for Indian system, metric unit, it is 23.6 kilonewton per meter cube. Okay. Now, what is the area? This area is your 1 times 0.5. So it is 0.5 square meter, right? Similarly here it is 4.5 feet square, right? If you multiply these two, this is the area. So if you multiply the area by this, by your unit weight, that will give you the weight per of the section, and that is, here it is 0.5 times 23.6 again multiplied by 1 meter. That is like 1 meter is considered. So that will be your what? 20, let us calculate that. 23.6 multiplied by 0.5, 11.8. So this weight of this section per meter is 11.8 kilonewton per meter of this section, right? Do you understand what I am saying? So it is 0.5, the cross sectional area, multiplied by the unit weight times 1 meter length. For 1 meter, this is the weight. So you can write there 11.8 kilonewton per meter is the UDL. Assuming this cross section is uniform all throughout. Whatever section is here, here is also same, here also same. Okay? So this is how it is. When you consider the same section, the unit weight or the load will be of this beam is uniformly distributed, and this is the self weight. You see, there are load for the dead load. When you consider dead load, the load, permanent load, one of the dead load is self weight. Self weight. So instead of having the short section like that, what you can do, you can show it with the help of a cloud or some short arrowhead. Okay, or in here, the American system, it is 0.15. This area is 4.5 times your 0.15. This will be your 4.5 times 0.15, 0.675. that is your kip per feet. So this is the unit weight. So instead of that, in American system, this value will be 0.675 kip per feet. This is what is the how you calculate the unit weight. Similarly, when you have the uniformly distributed load like that, suppose you have a beam. You have a beam in a building. You have a beam, and on top you have got a wall. Same length. Suppose the length of the wall is h. It's made of brick. Okay, the beam is here, right? So this load, you can find out the height and the thickness. Suppose the height is h, it will be like this. This is height, the thickness is t is the thickness, multiplied by h times t times h, multiplied by the density or unit weight of the wall, that will give you, and multiplied by the 1 means 1 meter, or is a foot, so 1 foot. So that will give you the unit weight, that is a uniformly distributed load. That is how it is. On this uniformly distributed load on this beam. So this is what is happening. So uniformly distributed load is the which is equal intensity is all over the beam. Sometimes some not self weight. In some cases, if you have a beam, it may be partially loaded like that. The uniformly distributed load is not fully covered up to here, but it is partial. It is suppose certain length L1, L1 is the length. L1 may be anything, any length, and total span is L. Do you get my point? That is the difference. So it is not fully covered like here. Here this length is L. It is the self weight, it covers the whole thing. But in some other exterior wall, just like a wall, I explained the wall, right? The wall is say partial, the wall is there partially, not fully. Then this is the load. Load may be anything. So now what happens for bending moment and shear force if you have the uniformly distributed load? That is the today's discussion. We'll discuss it today, how the beam will behave for bending moment and shear force when the load is not concentrated. Yesterday I was talking about last time I was talking about concentrated load. If the load is point load, it is not point load, but it is uniformly distributed, then what will happen? That is our discussion today. You know what is UDL? What is uniformly distributed load? What is its source? How it comes into play? But today, say we assume it is 5. Make it a little bigger. 5 kilonewton per meter. Or I am taking the same value, 5 kip per feet. Remember, these two values are these two numbers are not same, and this span is say 10 meter or 10 feet. So now, first of all, what you have to do, you have to find out a reaction. That is the fundamental thing. Whenever you have a bending moment and shear force diagram, you need to calculate the reactions. If it is covering the whole span, and I told you in the last class, if the load is and the location is symmetric, then you can simply take half of that load coming there, half of load coming there. If not, if something like this, if you have something partially applied, or something like this, load is applied, two loads are, location is also different, say 10 and 5. So then you have to take moment of all the forces, including the reaction, all the forces about one point, either this point or that point, and make it equal to 0. That means the moment caused by reaction is equal to the moment caused by the forces. That is simple. That is what you have to do. Now, as because it is symmetric, we can simply find out what is 10 meter, what is the half of this whole thing. So what is the total load of the UDL? The 10 times 5. So total load is 50. So this is 5 kilonewton per meter. The length is 10. So 5, so total load is 1 meter has got 5 kilonewton, or 1 foot has got a 5 kip. So what is the 10 foot or 10 meter has? So 10 times of 5 is 50 kilonewton, or you can say kip if you consider the American system, American unit. So now 50 kilonewton, half of that is 20, half of that will be 25, and half of that will be 25. This is kilonewton or kip. I am considering different units, but values are putting the same for my easier in calculating my solving my problem. So now 25, 25. Now what happens? How to find out the reaction? What is the? This is the reactions are like this. What is the shear force? Let us calculate the shear force. Now, I told you this convention. If you are vertically up, vertically down, if you are calculating the values from left to right, okay, then the positive is upward. Upward is positive. Downward is negative. All the downward forces are negative if you consider the values from this way. But if you come from there, if you are calculating from this side, your vertical downward is positive, upward is negative. Just reverse of that. If you are calculating from there, the all upward force is negative. This force, if you consider the shear force from this end, this will be 25, will cause a negative shear force. But here on the left side, if you are going this way, 25 will cause positive shear force. Okay. So let us draw it. So this is your baseline. Now we are drawing, this is your, at this point, just left of that, nothing there. Just at that point, it is 25. Okay. So at a distance, you have, say, x distance. What is this shear force here? It is 25 minus 5x. 5 is the load times x. 25 minus 5x. Okay. So, and So consider this is x1. Second point is, suppose from here to here it is x2. So this value shear force will be 25 minus 5x2. So look at here, x1 is smaller than x2. So when you subtract smaller value from something, value will be higher than the bigger value subtracted. Okay, so that means it is gradually, so x is gradually varying, 0, 0.1, 0.2, 0.3, 1, 1.5, 2, like that. So it is gradually varying. So similarly your shear force also gradually reducing. Okay, what happens? Suppose what happens at the midpoint, 5 feet or 5 meter? So 25 minus 5, distance is 5, intensity is 5, so 0. See, at the midpoint the shear force is 0, but it is gradually varying slowly because it is 25 minus distance times x, and it is 0 at this point. Suppose that somewhere you are calculating at this 3 meter or 2.5 meter. Here it is 0, we know. Say the half of this, 2.5 from here to here. So it will be 25 minus 2.5 times 5. 5 is the intensity. So it will be, if you calculate this, 25 minus 2.5 times 5, 12.5. So it is 12.5, right? So this is 12.5. I'm using the calculator because to show you, I can undo it by without taking help of the computer calculator. But it is always better to use the calculator so you do not make mistake. So it is 12.5. So now this is half of that. Half of 25 is 25. So here now it will be further reduced going down, and at this point here it is maximum, here it will be 25 again. If you consider from the right to left, so 25 is up, so this is upward force is negative, so it is going down. All the downward force are negative, so all the downward force is positive. So 25 going down, it is reducing the value, gradually it's going up, and further going up and up again, it meets with here. This is your shear force diagram, positive, plus and minus. One thing I told you always, you see, the bending moment will be maximum at when the shear force changes its sign from positive to negative. So your bending moment will be at the midpoint here, maximum bending moment, always. And shear force is the thing you should also remember. Shear force is, in a simply supported beam, shear force is maximum at the support. Shear force is maximum at the support, and that happens. Support takes the maximum shear force, and the bending moment is maximum no matter what is the load, not at the support, somewhere in the middle region. You do not know exactly where, but it is somewhere here. But shear force is always positive, always maximum at the support. Got it? So now, what is the bending moment diagram? bending moment diagram, again you draw the baseline. So you see, when you have something like this, the beam like that, okay, what happens? It bends like this, forming like a cup, okay. So the beam, this beam is something, the moment will be something like this. It tries to bend like this, because the force, this force will trying to push it down, and these two forces will come up, so it will try to bend like a cup, and the moment is like this. So our sign convention was, or is, sign convention, this is positive. Our sign convention is, this is positive moment and this is negative moment. This is the sagging moment, it causes a sag, and this is a hogging moment, like a look like an umbrella. So now, as because this is this clockwise from left, this force will form a clockwise moment. So what is the moment? 25. Say if you consider at a distance x, it is, the moment here is 25x times minus this load is there, that will some cause some problem, okay. This is reducing, not like the constant. So this minus this load 5 times this load will be, if it x distance, this is the load we are considering here, it will act at the middle because this is the center of the load, okay. So this distance is x over 2, so it is 5 into x over 2. That means whatever distance is, that load minus that our load times the distance times half of the distance. So here this is your x, from here to here the load will be acting at the middle because it is all uniform, same load. So it will be acting at x, the distance from this to this load point, the resultant, you can call resultant, all the load, that is x upon 2, okay. So that is the moment at a point x. Look at this reaction. Suppose if you simplify it, it will be 25x excuse me, moment x equal to 25x minus 2.5x square. It is 2.5 x square. Okay, so this is the equation. When the x square is there, this is the equation of a parabola. What is the parabola? Y is equal to your equation is ax square plus, you can say, h. So this is the equation of parabola. Just the two constant there and x square. So it involves the square. So it will be a parabola. So when this, I told you earlier, when the shear force is linear, the bending moment is parabola, and maximum will happen at the midpoint because this is symmetric. This, as you see from here, the shear force is 0 there. So let us draw the bending moment. So bending moment will look like this, like something like this. This will look a parabola and closing in there and there. Why it is like this? The x is on the negative, with a negative, right? Whatever moment caused by this, it is reducing gradually. So it is taking a shape like that. Maximum will be at the middle. Okay, this is equal to what? 25. If you consider this equation, if you replace x by 5, so what is the moment here? 25 times x 5 from here to here distance minus 2.5 5 square. So what is the value? Excuse me. 25 times 5, 125 minus 25 times 2.5, 125 minus 25 times 2.5, 62.5. Let us check again. 25 times 5 minus 2.5 times 25, 62.5. This is your kilonewton meter. You see why it is like this? Because you are multiplying force by distance. The unit is kilonewton per meter, or if you 62 point, if you use SI American unit, it is keep feet. So this is the moment is 62.5. It kilo, because you are multiplying the force and distance. Force is in your kilonewton and distance is your feet. So the unit becomes kilonewton feet. But in the shear force, it is only force coming up or down, right? So shear force unit is always kip or kilonewton. So here if you say it is 25, that is your kilonewton or kip. This is the unit. But in case of bending moment, it is kip feet or kilonewton meter. Two units are multiplied, just like the distance and force. Okay, so this is the case. But one thing I would like to tell you, this is a general thing. What? Suppose instead of calling it giving it some number, we assume that is W. W is the unit load. What is the reaction if it is length is L? Okay, what is the reaction? Half of total load is WL, right? Total load on this beam is WL. So half will come there, WL upon 2, WL upon 2. This is the reaction. Okay, so you know that at the middle this is the maximum. So what is the distance middle? It is L over 2. If this is length L and this is half of L, correct? So what is the moment here? This distance. So if you calculate this moment there, this is WL, this is the reaction. Okay, you can say RA, if this is A, this is B, RA times L over 2 minus W times L over 2, this is the load, the total UDL here, they are acting at a half of this length. So it is L over 4 from here to here. So times L over 4. So what is R? R is WL upon 2. So what is the equation now? So it becomes, this is equal to WL square upon 4 minus WL squared upon 8, right? So this is become WL square upon 8. So this middle, if you do not express in terms of number, this is always WL square upon 8. This is a formula. This is a formula. The maximum moment of a uniformly distributed load is WL square upon 8. Always remember that. When you are an engineer, you have to come across a load like that. The uniformly distributed load covering the whole span. And what is the maximum moment at the middle? WL square upon 8. What is the shear force at the end? It is WL upon 2. Shear force. Shear force there, when you draw the shear force is the maximum at this point, these 2 points. So WL upon 2 is the shear force, moment is maximum, WL square upon 8. It's always there. You have to remember this number. Certain numbers you have to remember. Okay. Now, expressing the same thing for a concentrated load. Suppose concentrated load is something like this. Suppose I told you yesterday or in my last class, we discussed the concentrated load. I did not tell you that thing, but it is true. If you have got a load, a beam like this, okay, you have got the load at the middle, at the midpoint. W, it is capital W, uppercase. It is the point load. This distance from here to here is L over 2, from here L over 2. Total span is L. What is the shear force? What is the reaction? Half will, because it is symmetric at the middle, it is W over 2, W over 2. You don't have to take moment. Simply it is like that. So what is the shear force? Shear force is, maximum shear force is at the support. That is, maximum shear force is your W over 2. What is the maximum moment? There is no force in between these two. So what is the moment at this point? From this side or that way, you calculate that one. Because this force will go through this. The distance from this here to here is 0. So no, it is exactly at this point. So this will not cause any moment. 0. So only this force on the left or that force right. So total moment is maximum moment at the midpoint is WL over 2 multiplied by L over 2. It is WL over 4. So maximum moment for a concentrated load at the middle is WL over 4. Always remember that when a concentrated load is there. Suppose if you have a concentrated load at something like this, not at the middle, suppose somewhere here, not at the middle. These are the formula you have to remember. It helps. You do not know the reaction now. So it is the vertical reaction is 0. The horizontal reaction is 0, no nothing, because the loads are all vertically down. Had there been a force like that with a angle, so there would have been the horizontal component of the reaction, but there is no here. If the load is there like this, vertical load, it is the distance is A. This is B. A and B, total length is L again. L is nothing but A plus B. Right? So what is the reaction here? Remember, I told you that it is easy to find the reactions there. Here the reaction is more, here is less. Right? What is the ratio of the reaction here? Because it is closer to that. So here reaction will be W times A multiply, opposite. Here it is bigger. So it is, you see, you can write the reaction straight away without taking moment. If you have a condition, it is higher here, closer to this reaction. So it is, and this value is higher than, so B is bigger than A, right? A is smaller than B. So B is smaller and this value is higher. So without calculating, you can say WB, higher value, divided by what? What is the ratio? Divided by L. WB by L, and here the reaction will be W times A so here less share of the load goes there, higher share will go there. The value is automatically in a different way. You see, W times B over L, W times A over L, and L is equal to A plus B. Okay, so what is the moment at the point? Shear force is maximum. Which is the maximum shear force? This is maximum because this shear force is higher value. So this is the maximum shear force will be maximum shear force, your W B over L. L is the total length, or A plus B. And maximum moment, that is what we are going to calculate. Okay, maximum moment, there is no force in between. So whatever moment caused by this at this point, that is the moment here under the load. So this load, and also another thing you should remember, when you draw the shear force diagram, the shear force diagram is like this. Remember that? It will come down. This is your W over B L, and W comes in, and this is the reaction, W A over L, and this is the shear force. This is positive, this is negative. And as you know from our last lecture, that is, the shear force is like this. When the shear force changes its sign from positive to negative, this is the point. Here the moment will be maximum. And it is, when the shear force is linear, the constant, bending moment is linear, like this, like a, see, slanting line, like this. So this is value. What is this value? This value is the maximum moment, or the moment here will be WB times L, or divided by L times A. That means WAB over L, or you can write this, you can write WAB divided by A plus B. A plus B is nothing but your L. This is the maximum moment here. W A times B divided by A plus B. This is a standard equation. Okay? So you remember that. It will be easier for you to solve problem later. Okay? This is what is all about. This is simple. Bending moment and shear force diagram is simple. By looking at it directly, you can say what is the value. Consider load, it is, shear force is something like this, constant value until the next load comes in. The moment is linear, and wherever the shear force diagram changes its sign from positive to negative, that is the place where you get the maximum moment. Always like true. Shear force is maximum at the support. Out of these, whichever reaction is more, that is the maximum shear force. And moment here, in this case, where the shear force changes its sign, there your moment is maximum. And so you understand something today. Probably next class. Today I want to conclude it here because I don't like to take much of your time. So you can see the video in one sitting. You know, if I make it longer, you have to watch it later. You cannot finish it in one sitting. Then you have to again start from beginning, or you have to remember what you saw earlier. So better to make this video short so that you can see it in one sitting and understand something. I don't like to confuse you with a lot of information. Understand? If you learn so many things at one time, you will forget, or you do not know what I am talking about. So I am making it simple, but next video I'll be talking if the load is partially loaded like this, similarly something like this, and also a constant load is a combination of both, partially uniformly distributed load and a constant load somewhere here, or the constant load somewhere there. It will behave differently. It is not the same. It is a combination, it is a complex. Then you have to find out the moment at these 2 points by taking moment about 1 point. Suppose if in a case like this, your RB and RA, you have to take moment about all the vertical and downward force and upward force moment at this point. So that way you calculate RB. When you get the RB by summation of moment equilibrium equation using that, then you can RA you can calculate by subtracting it these equations. Summation of vertical force equals 0. With that equation you can find the RA. Once you get the RA and RB, the reactions, we can draw the shear force diagram, or from here to the then whenever you shear force changes its sign, that is the point where your bending moment is maximum. And this is all for today. I hope you understand. I don't like to cover a lot of things in one day. So next videos I'll be discussing about the complex loading like this. We have to go a long way. I want to discuss all the different cases of bending moment and shear force diagram, so that you must score 100% in your exam. Okay? Because always there is a question on bending moment and shear force diagram. Always, sometimes twice, sometimes 2 or 3, like that. And it is a question, this is type of thing you'll come across in your practical life. Now also we calculate the bending moment and shear force diagram in our design. Okay, we have to find out what is the maximum shear at this point. What is the maximum moment, like that. It is always there. So if you have clear conception, your idea is clear, then you will be a very good engineer. Thank you very much for watching me. I appreciate it. Thank you very much. Bye.